And we're about to get started in here. This talk is called secuBT, Hacking the Hackers with User Space Virtualization. It's being given by Mathias. He is pursuing his PhD at ETH Zurich, and he is interested in speculative optimization of multi-core processors, among other things. He's worked on a project called fastBT, a dynamic binary translator, and decided that some of the work he's done on fastBT could be applied to computer security and malware analysis. So he has developed it into secuBT, which he's going to give you a little discussion about now, about how it works and how it can be used to analyze untrusted binaries without messing up your computer. So if you'll please give him a round of applause, and we'll let the talk begin.
Thanks very much for the introduction. I'm really surprised to see so many people here. It's for the first talk in the morning. For me, it's the sixth time at CCC, and it's the first talk before noon that I'm attending, so I'm really surprised to see so many faces here. But let's start. I'm going to talk about secuBT, a user space binary translator that we developed at ETH Zurich, and our motivation is to virtualize and encapsulate running programs, because we think this is kind of important to have a virtualization based on a program level in user space. We want to sandbox server processes to guard against unknown software vulnerabilities, and we want to guard and protect the execution of untrusted code so that we can run untrusted code on a system without really sacrificing neither security nor performance. And we want to offer different security contexts on a per user level and not on all programs that run per user have the same possibilities. If we are in user space and a user starts a program, it looks a little bit like the picture on the slide. We have the untrusted code or the program that runs in user space and has all the capabilities that are available for the specified user that it runs under. And we can execute any system call and branch to kernel space whenever we want to. So the programs can execute any system call. It's no custom tailored selection or cut down selection on the things the program really needs, but just a fits all approach where we can execute any system call that is exported by the kernel and is available for that specific user. Different security vulnerabilities in these programs can be used to execute unintended system calls. And these system calls are normally not typical for that specific application. And then we will kind of see that, well, some unintended system call is executed and something bad happens. But the current flow of security or risk analysis or risk patches are that we have patches that were downloaded or software that is updated, and software is restarted, and then we kind of fix the security vulnerability. But these are all reactive forms of security, where we discover something that is in the wild, we develop a patch, we test that patch, we upload that software on a central repository, people download that software and install the patch and the update. But during that time window, we are open for an attack. So patches are kind of a reactive form of security, and we want to get around that. The solution that we propose is user space virtualization. We use a virtualization technique in user space to encapsulate a running program with an additional layer of security. All the executed code inside the user process is checked and validated. So the program cannot execute any unintended instructions or system calls. All the code in the untrusted program can be wrapped or modified and is checked. Through that checking and validation, we can intercept all system calls and validate them before execution. That's why we can redirect these system calls to fake system calls, or allow them, or kill the program. There are many different possibilities that we have there. So user space virtualization with the additional level of virtualization enables and activates a proactive form of security where we can run untrusted code in user space with only a subset of available system calls. Whenever the program executes an unintended system calls or tries to execute unintended code, override some buffers, or does some other malicious stuff, we can kill that program, we can send a bug report, we can send an email to the administrator, or we can do something else. So what actually is user space virtualization? User space virtualization is implemented through dynamic binary translation. Dynamic binary translation is the art of adding, removing, or replacing individual instructions during the runtime of a program, where we have control over all user code instructions. So we check all these instructions, copy them to a safe space, and let the program execute the safe copied instructions and translated instructions. For example, VMware uses binary translation for full system virtualization. They guard specific instructions that are available in the ring 0 and translate them into their own code and wrap the program like that. But VMware uses binary translation for full system virtualization. We use it only for process virtualization to add an additional layer just around one process and not around the whole system. We want to keep the overhead minimal, and we just want to virtualize a process, not the system. So we implemented secuBT, which implements a user space sandbox using dynamic binary translation for the virtualization layer to wrap that program. Through that virtualization layer, we implement some form of privilege separation to guard our binary translator so that the user program cannot access data structures or cannot even get a pointer into the binary translator or into the private data structures of the binary translator. The user program doesn't even recognize that it is virtualized and translated. On top of that virtualization layer, we add a system call interposition framework. This system call interposition framework allows the binary translator to check and validate all system calls based on a list of allowed system calls and some user space function which check the arguments, the pointers, and can do some specific analysis on that. This ensures, together with the virtualization layer, that the program cannot break out of the virtualization layer. So after a short introduction, I will discuss the design and implementation of the binary translator and the security framework. I will first discuss the user space virtualization component through the binary translator. I will discuss the basic translator, give you some information how binary translation is done, what things are needed and all these things and how it works. Then discuss some specific optimizations to make it fast and competitive. After that, we will discuss some specific security hardening features that are needed so that the program cannot break out of the virtualization layer. And then we will go into detail about the system call interposition framework. And in the end, I will show you performance numbers, the demonstration, and conclude. So binary translation can be used as a program instrumentation tool, and this is kind of how I got into binary translation. I was working with some optimizations and trying out different things, wanted to add specific instructions, wanted to wrap some instructions, and just rewrite some program parts. I looked into all of the different libraries that were available, and in the end I thought, well, all of these are really limited or closed source or both. So I really got to the conclusion that I had to write my own library to do that binary translation thing. And there are two different takes on binary translation. Either you can do static